If you watched any of the other parts of this series, you know that I described the atom as a tiny tornado of energy. The primary purpose of this presentation is to convince you that I am right about the nature of the atom. In every part of this series, I have stated that at the fundamental level, energy can only take three forms. First is the energy ocean. It fills the immensity of space. It is comprised of photons of light, which is entirely a particle phenomenon. Secondly, atoms, indeed all particles, are tiny tornadoes of energy, spun from the photons of light that make up the energy ocean. Different sizes and shapes of tornadoes represent the various elements. And third, our velocity through the energy ocean keeps our tiny atomic tornadoes spinning, like a pinwheel held outside the window of a moving automobile. There are no other forms of energy at the fundamental level, and no particles have any other form than that of a tiny energy tornado. I know that these fundamental forms of energy are truly the foundation of our existence. I also realize that it is different from the speculation of scientists down through the ages. As I attempt to convince you of the truth, I will also help you see the folly in some of the earlier speculations. In his book, The God Particle, Leon Lederman acknowledged that the fundamentals are too small to ever observe directly. But to justify the continued scientific investigation into the fundamentals, he offered an analogy about aliens and soccer. Some visitors from another planet came to Earth. They had a unique problem with their vision. Anything with patterned black and white was invisible to them. They watched an entire soccer game and observed people running around the field. Occasionally the crowd erupted with cheers and sometimes moans, but they could not see the soccer ball. A few times they saw the net distort as if something invisible hit it. In spite of the fact they could not see the soccer ball, they managed to understand many of the rules of the game. Even though scientists can't see the fundamentals, they have continued to investigate as best they could, and they have learned some things. Following is a list of 15 things that we now know about the atom, and I have added some comments. Number 1, space is not empty. Therefore, an atom must exist and operate in space that is full of something, probably energy in some form. Number 2, the atom apparently contains a lot of energy in some form, per equation E equals mc squared. Number 3, the atom must actually be made of energy in some form. Number 4, the atom must be able to absorb or lose energy to change its mass along with changes to its velocity, per the equation to the right. Number 5, all the laws of science must remain the same regardless of the speed of the observer. Therefore, velocity must be fundamental to the atomic structure. Our current velocity through space, c squared, must establish the current size and mass of all our atoms. The relative appearance of the atom, even though we cannot see it, must remain the same as its mass changes with velocity. Otherwise, its chemical and/or electrical properties may not perform identically. Number 6, the atom has a spin quality. Number 7, the atom can be split. Number 8, mass can be added to the atom to make isotopes. Number 9, the atom can be annihilated, more easily so with smaller atoms. And number 10, the atom vibrates. Number 11, the atom appears to exist within a cloud of electrons. Number 12, the atom appears to have a positive charge. Number 13, the atom exhibits both electrical and magnetic properties. Number 14, the atomic structure has to account for all the elements and isotopes. And number 15, the atomic structure must be infinite to fulfill relativity requirements. Now this is an arbitrary list and is based on my own reading from books written by scientists but intended for the general public. Others may know of items that could be added to the list, but these are adequate for my purposes. In my opinion, too little consideration has been made of the requirements that relativity places on the nature of the atom, and that's why I named this series of videos Relative Understanding. As I tried to explain the nature of light, I did it in the context of a relative situation. I will deal with the atom in a similar manner. If you had a rubber balloon with a rigid opening and held it outside the window of an automobile with the opening facing forward, you would see it increasingly inflate as the automobile's speed increased. Conversely, the balloon would tend to deflate as the automobile slowed down. Based on this equation, the mass of a particle increases with velocity, similar to the balloon example. Scientists are pretty sure that space is filled with something, so particles must be able to absorb that something such that the mass increases along with its velocity. And based on the corollary, the basic structure of the particle must remain the same, only larger and more massive. In the case of the balloon, the rubber skin would get thinner and stretched more tightly as velocity increased. At some point, the balloon would probably burst. Also, you would have to ensure that the opening was always pointed in the direction of the velocity. Since neither of those things seems to be the case when particles are routinely accelerated, we can safely assume that particles are probably not made like a balloon. In other words, an atom cannot just be a container made of one thing, holding various quantities of mass, something else. In order for a particle to get more massive without stretching and breaking, its very structure would have to be made from the same something that fills space. When asked what tiny fundamental particles are made of, scientists quickly respond, energy. They probably feel comfortable with that answer because of Einstein's famous equation, E equals mc squared, indicating that mass and energy are interchangeable. So we can probably assume that whatever fills the immensity of space is some form of energy. Scientists call it dark energy because whatever it is, they cannot see it. I will call it the energy ocean. We may assume that we are immersed in an ocean of energy. And since Max Planck discovered that energy can only change states in quantum leaps, we may also assume that the energy ocean is filled with particles of energy, probably of a quantum size, and in my opinion it would be illogical to assume that energy particles can only take one quantum leap, so we may reasonably assume that they are continually taking quantum leaps. This would mean that the energy ocean is filled with energy particles of all sizes, from the infinitely large to the infinitely small. And this would be required if relativity equations are believed to work without limits. Since atoms, electrons, and photons are too small to see with any microscope that scientists can even imagine, we need to imagine a microscope that can actually see such tiny things. I call it the magic microscope, a thought experiment microscope. Question number 1. What is mass? Well, consider Einstein's famous equation E equals mc squared. Mass, m, is a measure of the number and size of the smaller energy particles, E, from the energy ocean that are compressed into the walls of the tornado-like structure of the atom. So when we look through our magic microscope at an atom, we will see its tornado-like structure. And if we enlarged one of the tiny photon particles making up the wall of the atomic tornado, we would see its tornado-like structure as well. And likewise, a smaller photon making up the wall of the larger photon, and so on down to infinity. After the atom has been accelerated, based on this equation, to an observer it must appear to be proportionally identical. It would have to have the same number of energy particles from the energy ocean making up the particle, but they would all be proportionally larger. Everything would have to appear to be the same, even though we know that the mass of the particle has increased along with an increased mass of any of its components. Also, its rate of spin would have to appear identical. Based on Einstein's equations, we must be racing through the energy ocean at speed c squared. That would have to be what I call a foundational variable. Whatever the actual speed might be, it determines the current size of all of our atoms, and any atoms that might be used in a detector to measure the speed of light in a vacuum would always be the proper size to measure it as c. Velocity through the energy ocean sets the standard for our existence, which is why all the laws of science remain the same regardless of our speed. Velocity simply has to be fundamental to the basic structure of the atom. Question 2. What form does energy take to become a particle? If anything other than energy is in the particle, then increasing its mass by accelerating the particle through the energy ocean would logically change the proportional content of the particle. This would violate the corollary that requires all the laws of science to remain the same regardless of the speed of the observer. There can be no unchanging part of a particle when it is accelerated. It must all increase uniformly so that any relative examination of the particle would appear exactly the same regardless of its velocity. Part of the justification for continued high-energy particle research is the goal of smashing our way down to the fundamental unbreakable particle. But if such a particle existed, it would violate the notions of relativity. So, in all likelihood, there is no unbreakable particle. Therefore, the fundamental structures must be infinite in nature. Because scientists have no magic microscope, they can only guess what a particle actually looks like. Sometimes those guesses are spurred by observations of things they can see. The standard model of the atom was patterned after our solar system, with electrons, like planets, orbiting around a nucleus, like the sun. While many scientists are still working desperately to lend credibility to this model, it has far too many obvious flaws to accurately represent the true nature of the atom. The most obvious flaw is that it does not include velocity as one of its variables. Initially, the nucleus was assumed to be solid. When it was split, scientists had to scramble to imagine how and why the fragments stayed together. The orbiting electron notion had some initial math problems that could only be solved by assuming that each electron orbit was exclusive. And how one electron could tell another that this orbit was taken was never clearly explained. The notion of mass is unexplained, or only marginally believable. Other problems became more apparent when we consider splitting the atom. Still, it is an attractive idea that the fundamental particle structure will resemble in some way a physical phenomenon in nature that we can observe. The TV Weather Channel often features tornadoes. Obviously, they contain a great deal of energy, enough to level mobile home parks or even entire towns. They are known to draw into themselves surrounding material, cows, tractors, houses, people, and most anything else that comes close. They may not exactly vibrate, but they do tend to wobble somewhat. Perhaps that wobble might become a vibration if the tornado were smaller and moving much faster. Now, how does the atom vary its mass with its velocity? Well, we know that the atomic tornado draws in surrounding material as they spin, so they will logically tend to grow larger. But they also vibrate. Let's imagine what that vibration might do. When a flag is waving in a stiff breeze, you can hear it snap and pop as tiny cloth fragments tear off and are sent flying in somewhat random directions, fraying the trailing edge of the flag. Likewise, when an energy tornado is moving through an ocean of smaller energy particles, it might vibrate like the flag. This could explain nuclear vibration. The continual absorption of new particles might change the atom's vibration pattern, eventually causing it to snap off part of itself. This could be how nature implements the quantum loss of energy. Those tiny fragments could be the electrons that we used to think were orbiting around the nucleus. This emission of electrons would be a loss of mass which would compensate for the increasing mass due to the atom's continual energy absorption. So, with a constant velocity, the atom maintains a somewhat constant mass, allowing for minor variations between electron emissions. If we increased the velocity of the tornado, we could reasonably expect that the absorption rate would also increase, allowing the tornado to increase and continue to operate at a greater mass. Direction would not appear to be a factor since a tornado can absorb from all sides. Velocity could help keep the tornado spinning like the pinwheel held outside the window of a moving automobile. And the continual emission of electrons could account for the cloud-like notion of electrons surrounding the atom. There would probably be resistance to the motion of the tornado through the energy ocean. That would cause the tornado to slow down and get smaller. When atoms are bunched together, like planets and stars, the slowdown would likely not be as dramatic because of gravity and inertia. We would not notice the slowdown because all the laws of science would remain the same regardless of the speed of the observer. Perhaps the entire universe is really getting smaller. It might appear to some to be expanding because all of our measuring instruments are getting smaller. The primary purpose of relativity could be a cosmic trade-off, continually giving up some of our mass just to maintain our existence. It could mean that the universe might have started with more of a big shove to get it moving instead of a big bang to bring it into existence. It may also be why all the relativity equations include a velocity factor instead of an ignition factor. The shape of atoms might well be like that of a tornado. Tornadoes certainly contain a lot of energy. They obviously have a spin quality. They vibrate, if you could consider a wobble just to be a slow motion form of vibration. The tornado is a simple structure with no component parts, just the smaller energy particles that make up its walls. Its mass readily changes with velocity. Different sizes and shapes of tornadoes could represent the different elements and isotopes. They operate in space that is not empty, and they are made of the stuff that surrounds them. Besides all that, I already know that it is the correct answer. Question 5. What happens when we split an atom? The nuclear bombs and power plants regularly demonstrate that energy is released by splitting the atom. The unanswered question is this: exactly what are we splitting? What model of the atom could reasonably withstand a collision sufficient to break it in two while allowing its remaining parts to keep on ticking as smaller atoms? Splitting the standard model of the atom presents some interesting, even extraordinary stretches of the imagination. Picture the standard uranium atom with its myriad of orbiting electrons, all 238 of them, being split into two smaller atoms. Now the result is a release of energy and the formation of two new atoms, krypton and barium. This is one likely result. There are other possibilities. If we do not look too closely, this might seem reasonable, but let's further examine the nucleus of the atom. Supposedly, it contains a myriad of positively charged protons, all compressed together in a very tiny space, as shown to the right. Theoretically, they attract and hold all those 238 electrons in their respective orbits. However, all scientists believe that particles of like charge tend to repel each other. This would suggest that the nucleus should fly apart, but it doesn't. Supposedly, there's a mysterious strong nuclear force holding all those positively charged protons together against their will. This force is indeed mysterious because it not only overcomes the tendency of all the protons to fly apart, but it somehow still allows those same protons to attract and hold their respective electrons in their unique orbits. Out of respect for the almost 100 years that this model of the atom has been the standard, we will pretend that this somehow makes sense. Let's go ahead and split the nucleus. When a neutron splits the nucleus, it would seem an excellent opportunity for all those protons, held tightly together against their will, to escape, reunite with their designated electron, and move to the suburb to raise a bunch of little quarks. But wait, experience tells us that we immediately get a burst of energy and two completely different atoms, each with their own nucleus filled with half of those very same protons. Still compressed together in a very small space, still attracting their beloved electrons, but in new orbits above. The burst of energy supposedly comes from a portion of the imaginary strong nuclear force, whatever that is. If this kind of a reaction occurred in the real world, a mother with only one balloon and two crying kids each wanting it could simply pop the balloon and have two smaller balloons, each fully inflated, one for each kid. This, of course, would be a Mary Poppins solution to the mother's problem, and in my opinion, it is also a Mary Poppins explanation for any scientist who actually believes the splitting of the atom really involves such improbable antics as would be required by the standard model of the atom. Now let's take a look at what would be required to split an atomic tornado. And keep in mind that the various sized tornadoes represent the different elements. When a neutron splits the atomic tornado, the portion of the tornado that is directly impacted decompresses and bursts into the surrounding energy ocean. And this is the energy that is released. The two remaining parts of the larger tornado immediately become the two new atoms, just because they are already smaller tornadoes. No protons, no electrons, no mysterious strong nuclear force, just two smaller energy tornadoes. Wikipedia explains Occam's razor as a principle of economy or succinctness used in problem solving. It goes like this. Among competing hypotheses, the one with the fewest assumptions should be selected. Other, more complicated solutions may ultimately prove correct, but in the absence of certainty, the fewer assumptions that are made, the better. In my opinion, splitting an atomic tornado is a far better explanation than splitting the standard model of the atom. There are fewer assumptions, and that is better. Also, the existence and behavior of the strong nuclear force in dealing with the imaginary proton nucleus stretches our imaginations much too far. Atomic isotopes are routinely created by bombarding a nucleus with additional neutrons. So, considering the particle tornado concept, we might look to nature to see if the neutron equivalent, a smaller tornado, can merge with an atom, a larger tornado. Now, some weather experts suggest that such a merger might be possible, but sightings are very rare. Relative collision speeds necessary to create atomic isotopes are unlikely to occur naturally between two weather tornadoes. Nature may not readily confirm this merging aspect of tornado behavior. So the isotope issue is left to our imaginations. Is it more likely for a small tornado to merge with a large one than a small neutron to break through the strong nuclear force and join other neutrons hidden among the many protons without losing any protons in the process? In my opinion, the simpler tornado-like structure makes a better argument. Over the past several decades, more than $6 billion was spent in the design and construction of CERN, a high-energy particle collider in Europe. 22 countries shared the cost. Thousands of scientists have been involved in evaluating the data from millions of particle collisions. I suspect that some useful things might be learned from such a massive project, but some of its underlying objectives were to validate certain aspects of the standard model of the atom. That model of the atom does not measure up very well based on the current list of 15 observations, which are now generally considered to reasonably describe the atom's characteristics or behaviors. When smaller tornado-like particles are smashed, some scientists assumed that the remnants were all functioning components of the larger particle instead of just energy fragments. It was that kind of thinking that led to the notions of protons, neutrons, quarks, gravitons, gluons, etc. Each particle fragment required some logical explanation for its existence and operation, which led to some highly questionable speculations. You can name an energy fragment anything you want, but considering that each energy fragment is a functioning necessary internal component of the atom is not the most reasonable and obvious assumption. When an airplane crashes, investigators try to find and reunite its component parts to understand the reason for the crash. And this is reasonable because they know that an airplane is built using component parts. When a typical snowball is smashed against the windshield of an automobile, no reasonable person would assume that the various snow fragments are actually functioning components within the snowball. Most folks would just reasonably and correctly assume that the fragments were just snow. When you're dealing with particles that are too small to see, why assume that any fragments coming from those particles are components, like those from an airplane crash, instead of just fragments, like those from a snowball? In my opinion, scientists, government agencies, and other funding organizations would allocate funding for basic research, that's fundamental particles and forces, more wisely if they based their grants on atomic theories that more reasonably explained the items that were on the list. In other words, if a particular atomic theory does not explain many list items or does not explain them very well, it probably does not deserve much scientific attention or research funding. On the other hand, if the theory explains many list items and explains them well, it probably deserves more scientific attention and research funding. My explanation of fundamental truth may seem like a theory to most scientists because they have never before had fundamental truth to guide them in their explorations of fundamental things. Some scientists have gained fame and respect because of their convincing arguments in support of their favorite theories. It will be difficult for them to accept fundamental truth. But if this planet is to remain fit for human habitation, some scientists will need to look past the early speculations and see the merits of fundamental truth as I have explained it. My explanations are conceptual. I tried to explain how fundamental things actually work. Scientists still need to develop useful equations and establish basic engineering principles so that the fundamental truth can lead to the changes necessary to keep this planet habitable.